starting. So we're going to continue with 6.1, inverse functions. There are a couple of examples that we skipped that let's go back to and make sure we know how to do them. Okay, what do we do here? You guys remember?
Substitute y in for x and then solve for y. To find the inverse. Oh.
No.
So you mean start with x is equal to y cubed over 4 plus y minus 1?
Yeah, but can we do
It's going to be really hard to solve.
just set that equal to 3?
Yeah?
Set inverse, set like make f inverse of 3 equals x.
Right, you want to find it? Call it something. Then you can take f of both sides. Different color size. You set that to be the case, and then you just take f of both sides. And we have a rule that says f of the inverse is just gives you the original function, and so this will be f of x. And so now we have 3 is equal to x cubed over 4 plus x minus 1. What do you guys think? Now remember, so here's where you can kind of guess things, but at the same time, know that for the inverse to even work, the function has to be 1-to-1. Right, so once you guess the right number, you don't have to worry about, is this the one I should be guessing? There'll only be one answer. So once you get the answer, you know that's the answer, right? Because it's going to be a 1-to-1 function. How would you think of getting to that answer? Ideas?
You add 1 and then you multiply by 4 and then you factor on x and then it's x squared plus the 4.
Yeah, so last time there was no fraction. It was kind of easier to see, oh, we just had 1 plus 1 plus 1 or something like that. But here, there's a quarter there, okay? So I probably want to get rid of that first. But you can add 1 to here. And then multiply by 4. 16 is equal to x cubed plus x. Plus 4x. Now can you see something that would work?
And then you factor out the x and then you have x squared plus 4, right?
Would that help though, to do that? I mean,
Oh no, yeah.
factoring is never something you really want to do. When you want to factor something to kind of figure out an answer, you have to have a 0 on the other side, right? Because when you do that, you're taking advantage of the 0 factor property. Yeah?
Did you just guess and guess that the
Yeah,
x
what
is
would you guess?
I would guess 2.
2. 2 seems like a good thing to work. And again, remember, this is the rational roots theorem. All right, so if I have x cubed plus 4x minus 16 equals 0, the guesses I would make would be the factors of this guy. So I'd guess things like plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. These were all the possible options for a nice answer. So you'll kind of start. You can clearly kind of see that 1's definitely not going to work, so you'll kind of ignore that, and then you start by plugging in a 2. Right? So it's not just totally random. There are some strategies you can use here. Right? And so, yeah, plug in 2. If x equals 2, you'd realize that here, that if you take 2 cubed plus 4 times 2, that gives you 8 plus 8, that gives you 16. So this means that f inverse of 3 is equal to 2. That's a part of, well, that's what we were after. Manipulation is also something you're going to have to be very good at in this class. So now you can imagine, we were talking about quizzes. Now you can imagine, let's say 2 students were doing a quiz, and one student sat there trying to guess the numbers that would work in this, versus another student sitting there trying to figure out the numbers that would work in that. Who do you think would run out of time? You know? Sometimes it's about manipulating something, changing the environment to suit your strengths. So you know about the rational roots theorem, so you'll probably want to get things in a form similar to that. No fractions, all whole numbers, where you'll know exactly the kind of numbers that you can guess. It'll make things easier for you. Okay, so a lot of times it's about, you don't always just take things as given. Sometimes you mess around with things, and you'll get into a much nicer situation. Just another thing time pressure can force you to do. Now it forces you to worry about, is there a more efficient way to do what I'm doing? You know, don't have forever to do it. I got like a minute and a half on this problem. I need to be efficient. I need to, and that itself kind of breeds this kind of mathematical maturity where you can kind of see things, you know? F of x equals sine x. Find f inverse of a half. This is probably something you know by heart. Yep.
So based on what we did for the last one, said sine x equal to 1/2.
Where is sine equal to a half?
Pi over 6.
Pi over 6. F inverse of 1/2 equals pi over 6. That is something that you should have memorized, but we will deal with trig later, and I'll go over some things that I expect you to remember from trig, and we'll look at this more closely. But let's move on. Calculus with inverses. Last time we saw the following theorem. If f is a one-to-one invertible differentiable function and f inverse is differentiable at x equals a, then we actually have a formula for the derivative of the inverse at a certain point. It's 1 over the function's derivative, f inverse of a. We derive that by the chain rule, by taking that relationship that f of f inverse of x is equal to x, differentiating that equation using the chain rule, which by the way is it's kind of employing implicit differentiation, which was on the quiz, and you will end up with that formula at the end of the day. So let's actually use that formula to figure out the inverse. So this is again, sometimes you can't find the inverse function in general. Sometimes if I give you a function and I say, find the derivative of the inverse at this point, what you could do is you could switch x and y, solve for y, you can get the nice function, then you just differentiate that function. But there are times when solving for the other variable is difficult and you can't do it. But you do know it at a specific point, you can find it. And that's a formula that can help you. So let's actually do a couple of examples here. F of x equals square root of x minus 2. Find the derivative of the inverse at the point 2.
That's not sure.
sorry, we know that the inverse derivative at the point 2 is going to be equal to 1 over f prime of f inverse of 2. So the first thing now we're going to do is find f inverse of 2. How would you find f inverse of 2? What we did before. This is basically what you're going to say, right? So f inverse of 2 equals x. This means f of x equals 2. This means the square root of x minus 2 equals 2. This means x equals
6.
x equals 6. There's a bunch of 2's there. So f inverse of 2 is actually 6. This means that the inverse derivative at the point 2 is actually 1 over f prime of 6. And so now simply we find f prime of 6. Now we find f prime. F prime would be equal to, how do we differentiate this?
1/2 x minus 2 to the negative 1/2
Times 1, right, because of the
yeah.
chain rule. And so this means f prime of 6 is going to be 1/2, 6 minus 2 to the minus 1/2. What is that going to give us? 1/4. This means that the derivative of the inverse at 2 is 1 over 1/4, which is 4. By the way, you can note that this is a function that we could have found the actual inverse function. In fact, let's actually just do that quickly. So we know that f of x equals the square root of x minus 2. So if we switch x and y, we would have x is equal to the square root of y minus 2. This would mean that x squared plus 2 equals y. And so this means that f inverse of x is actually x squared plus 2. And so we can actually take the derivative of that function, which is 2x. And so we can get f inverse prime at 2 is 4. Right, so that's another way. But the issue is, finding this function is in general not something you can do, but if we're only at a point, we don't really care. Any questions on this? This would be the main method, because if I put a problem like this on a test, it's going to be something where it's very hard to find the inverse function, because then teaching you that whole formula would make a difference. Example. F of x equals x to the 5th minus x cubed plus 2x. Find f inverse prime again at 2.
Thank you.
Yes?
Just quickly, if you do that way, you don't have to go the avenue of the 1 over f prime of the inverse. You can just take the derivative of the function you found as the inverse, right?
This will be if you can find this, then yes, you could just differentiate that and
Okay.
plug it in.
Okay.
Yeah.
Alright.
It's just that a lot of times finding that guy is hard or
Okay.
impossible.
Alright.
So we're even pushing the boundaries here. There's a theorem in mathematics that says there is no general formula for solving polynomials of degree 5 or higher. Right? We have actually formulas for everything up to the 4th degree, but it's actually impossible to find a formula for anything 5th degree or higher. And so once you're dealing with even simple function like a polynomial, if the power is high enough, this option becomes unviable automatically. And so you really need to know how to actually guess at a point. And you might be saying something like, well, that seems like a cop-out. What's the... Okay, I know it at a point, but I don't even know the original function. Well, the idea behind that is that in real life math is messy. It's not as straightforward as you might notice in calculus, but we can get around. Knowing about these ways, we can actually extrapolate other things. So if you're doing, for example, research, and you somehow want to approximate this function, you'll be able to do it point by point. And just have a computer just plot points for you. So you might not know the formula, but you can get a graph if you want, just by finding it point by point, and just have some algorithm running through. Solve all these equations by guessing numbers, you know? And a computer can do that fast. It can get thousands of points plotted for you in a couple minutes, and you'll be able to see things. So being able to find something at one point is actually a very powerful tool. So it's important that you know how to do that, because function, you're never going to go into the real world and the function that's so important that you need to figure out is going to be some polynomial. It's not going to happen. So, yeah, let's do this. But the ideas here are important because you extrapolate them and you abstract them to deal with more complicated situations. Okay, so you know, f inverse prime at 2 is just 1 over f prime of f inverse at 2. Okay. And here I wouldn't even attempt trying to find the inverse function because that's a 5th degree polynomial. It's probably not going to work out. And so what we can do here is first find that f inverse of 2 that I want to plug in. Okay, can anyone tell me what x is? 1. F prime, you differentiate that, that's 5x to the 4th minus 3x squared plus 2. You plug it in, x equals 1. 5 minus 3 plus 2. Huh? That's a quarter. That's the end of 6.1. Homework for that is due on Friday. But 6.1 is really culminated on problems of this type. So if I'm going to be testing you or quizzing you on 6.1, for the most part, you can expect to have a problem kind of like this. Right, I'm going to give you a random function, ask you to find the derivative of the inverse at a certain point, and you kind of go through. The next thing we're going to do is move on to 6.2, which talks about exponential functions. And after that, we'll move on to logarithmic functions, but I figured it would actually be nice to actually go back to the pre-calculus of these rules and actually look at those first preliminaries for 6.2 to 6.4. So we're going to be talking about exponential functions and logarithmic functions, and the rules of exponents and logarithms will apply. So I decided I wanted to remind you guys what some of these rules are. So let's talk about the laws of exponents. So these are how we deal with things that have powers in them. Exponents is just another word for power. Right? That little number that we write to the top, and hopefully everyone here knows what that actually means. X to the 5th means multiply x by itself 5 times. And blah, blah, blah. Okay. And then we can kind of make abstractions of these rules to get a bunch of other rules. So let's actually ring some of them off. If I have x to the a times x to the b, what is that? You add the powers. Okay. One thing I want to emphasize here is that these rules work in general, even if, for example, say, the base I made a constant and the power I made the variable. The rule would still apply in exactly the same way, and that's what's going to be important. So I want you to know what the original rules are, so when I extrapolate them to a different context, you can kind of follow them, right? So it doesn't matter if your base is a variable and the power a constant, or the other way around. These rules still apply in the line of exponent. Okay. X to the a divided by x to the b. X to the a minus b. What is x to the a, and I raise it to the b? Multiply. What is x raised to the 0? 1. Of course, your x cannot be 0 for this. You may remember that they use this rule to prove that rule. It requires division, and so 0 doesn't work here. 0 to the 0 is indeterminate. Okay, it might be silly. X to the 1 is? X. What about x to the a over b?
B. A. I mean x.
And in general, you can switch these. So you can take the b root of x raised to the a. If x is positive, can be switched. If your x is negative, a few things can come into play if your radical is even and all that stuff. But sometimes it might be easier to do one or the other. And if your x is positive, you can actually do that. It's not going to be a problem. We all remember this? So I usually had a mnemonic called flower power to remember where the radical goes and the power goes, but I guess I don't have to say that here. What else about exponents would we need to talk about?
Negative
Multiplying them, dividing them. Negative exponents, yes, very important. If I have x to the minus a, how do we consider that? I think it's over. Let's look at logarithms. Do you guys remember covering logarithms? Did you do it in Calc 1? You guys did it in Calc 1? In pre-calc?
Like natural.
Okay, so you guys did do this, okay. Let's actually just remind ourselves though. I want to make sure everyone's on the same page. How do you describe a logarithm? What's a logarithm? Logarithms are powers, they are exponents. It's kind of just looking at it then from the other avenue. So the notation here is logarithm, the base is the number that would go here. The base is usually going to be greater than 1. The number goes here, and we say that is a power. In fact, that is the power that we need to raise the base to in order to get that number. So for example, log to the base 2 of 8 is equal to 3. Why? You have to raise 2 to the power of 3 in order to get 8. That brings us to the first rule, which can be taken as a definition of a logarithm. It says that log to the base a of b equals c if and only if a raised to the c equals b. So that's the first rule of a logarithm. Rule 2. That idea leads us to a lot of things. For example, if you have log to the base a of x and you're multiplying it by y, what can you do with that? You can add the logarithms, log to the base a of x plus log to the b y. So logarithms turn multiplication into addition. And it's kind of, again, it's the reverse. When you're multiplying things, you add the powers. The logarithms are the powers, so multiplication becomes addition. Right? It's one of the reasons why logs are very nice. They can simplify things for you. They can turn multiplication into addition. They can turn division into subtraction, right? Because of this rule. It's log to the base a of x minus log to the base a of y. They can turn powers into products, right? Because when you raise a power to another power, you actually multiply the powers. So rule 4 is if you have log to the base a of something to a power, you can take that power down in front and multiply the log. Right, these are rules that are going to come into play later on when we're deriving some rules of calculus, so I do expect you to remember these guys. Rule 5 is called the change of base formula. Does anyone remember that formula? How to change the base of a logarithm? Log to the base a of b, I can actually, if I don't like the base a because it's difficult to work in that base, I can actually change the base. This is going to be important because there are certain bases that are nice to work with in calculus, and so if you're given a log in a different base, you want to convert the base in order to do calculus with it. Yeah?
Is it log of b over log of a?
It's log of b over log of a, yes, and the base, you can actually choose it. C is a conveniently chosen base. If there's a base that's convenient for you, you can just choose it, and taking that ratio is the same as looking at the original logarithm. Rule 6. What is log to the base a of 1?
0.
0. Log of 1 is always 0, because any base you raise to the 0 power in order to get 1. What is log of 0?
Doesn't fit.
Undefined. Right? If I say 2, what power can I raise 2 to in order to get a 0? There is no such power. Right? You can't raise a positive number to any power and get 0. Right? If you raise to a negative power, you get a division. If you raise to a positive power, it just multiplies that thing repeatedly. Right? So log of 0 is undefined, log of 1 is 0. Really the first 5 rules are the super important ones. Every rule I'm listing now are things that it's good to know them right away, but you can actually derive them from what we have so far. And literally everything can be derived from this below. maybe they prove that for you in pre-calculus or maybe calculus, but I'm not sure. Rule 8. Which one do I want? Let's say log to the base a of a to the x is equal to x. Why? Because the logarithm of a number to a given base is the power you have to raise the base to in order to get the number. What do you have to raise a to in order to get a to the x? X. Rule 9. This one is a little bit trickier to prove. But if you have a and you raise it to log a of x, what do you get?
X.
You also get x. Right? That one's kind of strange, but how I probably prove it is you can take a log of both sides. I don't know what this thing is, so I can set it equal to y, for example. And because of the previous rule, this guy, the log and the exponential cancel, and this gives me log to the base a of x equals log to the base a of x. That's not set a to the log base a of x equals y, because what I just did might seem circular. Now I take the log of both sides. This one becomes log to the base a of x, and this is equal to log to the base a of y, and so this means that x equals y, which is the original function. And this happens since log is a one-to-one function. You can actually graph logs by plotting all the points for the powers, and you'll realize that it passes the horizontal line test. There's something very important that rules 8 and 9 tell us. What does it tell us? If you take both of those rules together, what does it mean?
The logs and exponents are inverse functions.
They're inverse functions of each other, right? Remember when you plug one function into another and you get the original input, and that works in either way? If I plug an exponential into a log, I get the original input. If I plug in a log into an exponential, I get the original input. Those two things together means that these two guys are inverse functions. And that's going to be important for deriving a lot of things. So the functions y equals log to the base a of x and y equals a to the x are inverses of each other. So if we know about one, we kind of automatically know about the other one. Notations for this class. If I write log x and I don't write the base, what does that mean? It means log to the base 10. If I write ln of x, what does that mean? It's called a natural log. It's log to the base e. E is a constant. It is a very important number. I will define later when I actually get to 6.2. I will define that. Okay. Note in advanced calc and above. If if you're reading a high-level math book and the math book writes log x, they actually mean ln. Right, so I don't want you to be confused about that. So normally, things when they neglect to write a part of a notation is because they're thinking of that as standard, right? That's the standard thing that no one's going to mention. Mathematicians work in base E when it comes to logs all the time. So when you get to a certain level, when they write log, they mean base E. They'll always mean base E. So log is kind of the standard log, and it actually depends on the discipline, for example. So if you're a computer scientist and you write log, you mean base 2, binary, ones and zeros, right? You're counting by twos. Why log means log to the base 10? Engineering. Engineers work in base 10. They count in their figures. 1, 2, 3. So they work in base 10. Math people work in base E. Right? So log, depending on the context, it can mean several things. It will depend on the discipline you're in. But for now, we'll keep the engineering notation for this, and I will emphasize ln when I want to do log to the base E. And what that means all the previous rules I gave you can be rewritten to show things in terms of ln and e. So for example, I can say ln of e to the x is x, or I can say e to the ln of x is x, or I can say ln of, or I can say if ln of x equals y, it really means that e to the y equals x, etc. Right? So you can go back through all the rules that I just mentioned, and you can replace all the logs with ln's and all the bases with e, and the rules would remain intact, right? It's just me specifying a certain base. It's a base that it's more convenient to work with when we're talking about mathematics. Do we know about the graphs? Let's say I had y equals a to the x. Let me define a to be bigger than 1. What would the graph look like? A to the x. Did you guys look at the pictures? So what does it look like? Yeah?
I mean, it just goes up from.
Yeah, it goes like that. Right? It'll pass through 1 here. It does not touch the x-axis. That is what that looks like. From that picture, we can say several things about this. So for example, I can say something like, what is the limit as x approaches infinity of a to the x? It's infinity. As you're moving to the right, the graph keeps going up without bounding. What is the limit as x approaches negative infinity of a to the x? 0. So we can say things like that. We can also remember about our transformations. So in the same way, if I say y is equal to a to the minus x, what would that graph look like? Yeah, you reflect in the y-axis. Okay, by law of transformation. You change x to negative, it's a reflection in the y-axis. If I have y equals minus a to the x, that flips in the x-axis. So that would look like that. If I have y equals minus a to the minus x, that would look like that. Right? And from these pictures, we can talk about the limits again. We're going to actually go back over limits in this class, and we're going to do some more sophisticated methods about limits. But still, with limits, one of the most powerful techniques is knowing what the picture looks like and being able to talk about the picture. So for example, I would know that if I take limit as x approaches infinity of this guy, it's going to be negative infinity. Limit as x approaches negative infinity of this guy is negative infinity. Limit as x approaches infinity of that guy is 0, etc. Right from the picture, I can talk about the limits very quickly. Okay, so this was the graphs of the exponentials. This also shows that since you never actually touch the x-axis, there is no power you can raise something to in order to get 0. That's why there's no x-intercept. If we look at the graphs of logs, so let's say y is equal to log to the base a x. What would that look like? Well, it would look like this. Why? Because it's an inverse function. Draw a line x equals y, reflect in that line, you'll get this graph. It will pass through 1 to that. So again, we can talk about limits here. Limit as x approaches to 0 from the right. Limit as x approaches infinity. Log. What's limit as x approaches 0 from the right?
Negative infinity.
Negative infinity. X approaches infinity. Infinity. X approaches 0. Zero's right here. Does not exist, right? Because there's no left side. Remember, for a limit to exist, it has to exist from both directions, and they must give you the same answer. Yes?
Quick question, do you consider difference between does not exist and undefined?
No.
Okay.
But I do take infinite limits as existing. So for example, in this class, if I ask you something like, what is the limit as x approaches 0 of 1 over x squared? I expect you to write down infinity rather than it's undefined. Right, so that guy would look like this. So technically there is no number, but if you come from the right or the left, they both shoot up to infinity. So I do consider infinity to be an answer that should be deduced. Right. Does not exist means infinity or any numbers would not make sense to write down. We'll stop there. So on Friday we will start the calculus of exponentials and logarithms. Make sure you know these rules. And yeah. So the homework for 6.1 is due on Friday as well. And we'll start on 6.2.